Hello friends, the November 2022 exam paper has been released, so I wanted to talk about the review of the paper, and maybe I wouldn't go over like every detail of the problem, but I want to do the unholy version of the problem, so let's get to it, okay? So I think this is going to be great. So I got the idea from watching a recent music video, and this is one of the controversial songs these days, isn't it? And for me, sounds good. So once I was listening to it, and then I got the news that the 2022 November paper got released. So when I was reviewing, maybe I would do the unholy version of those problems. So let's get our business clean. Okay, so let's go. So yeah, for the first problem was working with the derivative, and then you had to work with the chain rule, right? So when you're working with the chain rule, I want you to memorize certain forms of the derivative. So let's get to the unholy version of this. So for this one, sure, you had to work with the, e fx, and if you differentiate this, my friend, you're absolutely right. I had to do f prime times e to the power of f prime x. Those derivative rules were necessary for this problem. But let's have a look at the unholy version of the question here. I'm not going to overdo this gesture. I just found it very fun. But yeah, I want you to memorize these. They are very popular functions to come up. And you know what? Yes, what you often do here is to work with the derivative of 1 over x as a x to the power of -1 and differentiate and use the power rule, right? And you may do so. However, if you memorize it, you can use it very quickly, you see. So for that one, it should be negative f prime of f squared. Yeah, if you memorize it, then it's so convenient for you to differentiate, you know what I mean? So for example, if I had a 1 over sine x, you know that it's the, cosecant x, and the derivative is the cosecant times cotangent. But if I didn't know, supposedly, what I can do is just simply write it as a negative sine squared x, and then the cosine x, right? So if you memorize this version of the 1 over x and its chain rule version of it, then it's very quick to differentiate. And what's another one that is very popular? The square root of x is very, very popular to come up. So it's good to memorize it. So what I mean by that is that, yes, you may do x to the power of half and then bring it down and subtract by 1, realizing the negative half is 1 over root x. That's absolutely fine for you to use it. However, if you memorize it, it just accelerates your computation, right? So yeah, very typical one is, suppose you have a square root of, who knows, so 3 minus x squared. And if I have to differentiate it, I wouldn't bother by putting it to the power of half because I memorized it, supposedly the rule of this. So it's going to be 2 square root of 3 minus x squared, and then boom, the derivative of inside by the chain rule is going to get me the negative 2x. Voila, then cancels out, then I have negative x over square root of 3 minus x squared to work with, you see. So it's good to memorize those three things. And one more, 1 over root x is also very popular, especially one with the optimization problem. So you may actually also memorize it. It's also the which version? The chain rule version of it. So that's the unholy version of the question number 1, right? It was just a simple exponent form, but there are many functions to work with the chain rule that are popular, so I want you to memorize them. One more, just application of that are going to be finding the stationary point of such, right? So if you have to find the stationary point of a function, you want to find its derivative and make that equal to 0, right? And when you do the differentiation for the square root of x, I don't want to do the x power of half. I want to use the memorized version of it. So let's get to it. So the derivative, right? So if we use the memorized version of root x was the 1 over 2 square root of x, right? So I'm going to do it. So it's going to be 1 over 2 root x, 2x minus 1, 3. And then the product rule, so plus square root of x, leave it as it is. And the second one, I'm going to use a chain rule for the product rule. So it's going to be 3, 2x minus 1, squared. Don't forget to multiply by 2, which is the derivative of inside by the chain rule. So the constant is going to change into 6. So that is great. However, yes, you're right. My aim here is to find this to be 0, right? So I want to solve the equation. For that, you need to factorize well. So let's try to factorize. So if I have to factorize here, what I want you to always try your best is to attack on the smaller things, smaller coefficient, smaller power. So what I mean by that is for the constant, I have a choice of a half. I have a choice of half and then 6. So for my common factor, I want to stick with the smaller numbers. I'm going to stick with half, my friend, here. You see? So I'm going to go with half. So that is a brilliant choice. And then you got the choice of the surge. You got the choice of a 1 over square root of x and square root of x. But for me, smaller power is better. So 1 over square root of x is in fact the same as you know, is x to the power of negative half. And it's definitely smaller than the positive half. So for me, it is natural selection to go with the 1 over 2 square root of x as a common factor. And then I got the cubic power and square power of that linear form. I'm going to obviously go with who? Yes, a very good smaller power, please. I'm going to go with, what is it? The 2x minus 1 squared, right? So that's great. Then I'm going to factorize, you see. So if I try to factorize here, the first one is pretty straightforward. Only the cubic is going to leave out only the power of 1 for that linear factor. That is great. If you divide 6 by half, that's the same as multiplying by 2. So it becomes, in fact, voila, just 12 like that is great. Then if you divide the root x by 1 over root x, you get x. So I'm going to leave it as just 12x from the second term. All right, that is great. It's not so bad, is it? So here, then I have, you know, the first factor, I will leave it as it is, right? So that is great. So I'm going to duplicate. And for the second one, my friend, what do you get? That's 2x plus 12x. That makes 14x. So that is brilliant, right? So it's well factorized. So I love it because I wanted to solve this for the stationary points. I'm going to let this to be 0. So then, you know, if this is a rational form, I have to take on the numerator, righto? So I'm going to go what, my friend? I'm going to go with, oh, x has to be either 1 over 2 or 1 over 14, right? So yeah, then the problem solved, right? And then you can verify the nature of the stationary point, right? So how would you verify the nature of the stationary point? Well, okay, that's a good question, actually. Yes, if you want to verify the nature of the stationary point of this one, you can do the sign diagram or second derivative, right? And what I want you to realize is that, yes, you know, it would be very difficult to differentiate once again, right? So it's because it's going to involve a lot of quotient rule and nasty factorization. So for me, I'm going to use the, what is it, the sign diagram, right? So only thing that determines the sign here is in fact the numerator, right? Because the denominator's got the square root of x, and for positive domain, it's going to remain the positive. So, and in fact, then, you know, 2x minus 1 wouldn't change the sign as well because it's a perfect square, right? And from the half, neighborhood is going to have the same sign. So if I put that in the ascending order of the stationary point of my sign diagram, I got 1 over 14 and 1 over 2. And I know that around the half, it's a perfect square, so it's going to be positive, positive. So unfortunately, that stationary point wouldn't give me either a maximum minimum, right? Or the local maximum minimum. But around 1 over 14, what you recognize is that it's a linear function with the positive gradient over 14. So it changes from negative to positive on his neighborhood. So I'm sure it's going to be decreasing, increasing, and then boom, I'm expecting to have, my friend, I'm expecting to have the minimum. So at 1 over 14, I will have the local minimum. So yes, the reason of bringing out this problem inspired from the paper, first question is, was talking about the chain rule, but there are various functions that is good to memorize, such as 1 over x, square root of x, and 1 over square root of x. And you can use the chain rule version of it, and often it leads to a good way of factorizing the forms for finding the stationary point or inflection point, because it requires not only the differentiation, but also the factorization. Okay? So that is great. Okay, and yes, for your convenience, so also, we're still unholy. Okay, we're still unholy. It's good to memorize. I don't think this derivative is given. Well, of course, that's given. That's the chain rule of the logarithmic function. But these three functions, I want you to memorize. Have I got it right? Yes. The derivative of ln cosine x. Oops, sorry. It shouldn't put the absolute value. Sorry about that. But yeah, ln cosine x. If you differentiate using the chain rule, you get a negative tangent x, and sine x is cotangent x, and this one is also good to memorize. I want you to please memorize. And then why is it good to memorize? Because then you realize, all right, then you realize that you can use the antiderivative. You can use the fundamental theorem of calculus to find its integral. So integral of a tangent is going to be who? Yes, negative ln cosine x plus c, negative ln absolute value of cosine x plus c. Integral of a cotangent will be the ln sine x, and integral of a secant x will be the ln secant x plus tangent x plus c. So those things are intertwined if you memorize the derivatives, and these are popular for the exam. So even if it's not in the booklet, please do memorize, okay? But here's the thing, you might say, oh, okay, it might be presented in the paper, but here's the thing, you're going to shorten the time of a deduction if you already know the form vaguely, right? If you have seen this once or twice, and if you see somehow with the integral of a secant x, you can associate with the logarithmic of a secant x plus tangent x, you see? So it's just good to memorize, right? It's good to memorize. And so, yeah, then I can find its integral right away, right? It's going to be then, remember, if it's got the linear substitution, you're going to take out the half, right? So it's going to be 1 over 2, ln absolute value of a secant 2x plus tangent 2x. You can write it right away because you already know its derivative form is giving you the secant 2x. So you can use the fundamental theorem of calculus. Okie dokie. So that's the unholy version of the question number 1. Oh yeah, there's even better. Even better. So, I think what that question could have been is to find the Maclaurin series of it, right? So, for the Maclaurin series of exponential, and then a lot of composition is very popular on the exam. So, on the question number 1 was just asking about to find the derivative of e to the power of x squared, but I think could have also changed in a way to find the Maclaurin series of it, right? And yeah, exponential function, that one is a standard form, right? So whenever you encounter a Maclaurin series problem, what I want you to remember is to avoid differentiating too many times. Of course, if the question asks you to find, the first, second, third derivative, and hence find the coefficient, you have to differentiate. But often, the problem to associate with the Maclaurin series is that you already know the standard form, and you simply use a composition, okay? So for example, we should know by heart that the Maclaurin series of that is, what is it, from 0 to infinity, x to the power of n over n factorial, and interval of convergence is all real, yes? And I want you to also remember the limit of 1 plus 1 over n to the power of n converges to e to the power 1, and I want you to also memorize, what is it, my friend, and 1 plus x over n to the power of n is also going to, what is it, exponential function. Right, so I want you to make sure to memorize this, and because I think it can also come up for the paper 3, who knows? But yes, our focus right now is to use it for the composition. Then it's lovely, right? Because I already know the exponential Maclaurin series, which is a sigma x to the power of n over n factorial, and you can just composite. So if you're compositing with the polynomial, with the power function, then it's straightforward because you can just plug it in and do the law of exponent. So here, law of power. So in this case, I'm going to have sigma, and I'm going to simply replace the x squared, right? So I can do the x squared to the power of n over n factorial. So that is great. So it's going to be sigma x to the power of 2n over n factorial is what I've got. But let's have a look at the unholier version of the Maclaurin series when you're compositing with a function like the sine x. What's the problem like the sine x? Because it's not the polynomial, it's not the power form. So you may think that I have to differentiate too many times to find the coefficient. You may also do so, but as you can see, the problem with that function, if you keep differentiating, you may have to do the chain rule, and then the second derivative now starts working with the product rule also. So it's a lot of derivative. But if you actually put x equal to 0, where the center is 0 for the Maclaurin series, you know that a lot of things are going to be actually 0. Okay, so it's not that bad. However, you also should practice to work with just the composition. So the whole point of compositing with the Maclaurin series with the non-polynomial function is that you can make it polynomial by using the Maclaurin series of the function you're compositing with. Let me tell you what I mean by that. So you already know the Maclaurin series of exponential function. We already wrote it like 4 times. So I want you to definitely memorize, but also the sine function you should memorize, right? It's also in the booklet. So the sine x, very good, is going to be sigma from 0 to infinity. It's odd function, so negative 1 to the power of n, x to the power of 2n plus 1 over 2n plus 1 factorial is what I've got. But here's the thing. Often what they ask you to do, my friend, when you're working with the Maclaurin series, compositing with non-polynomial function, they would expect you to find up to first 3 or 4 non-zero terms. They would ask you to find first, let's say, 3 non-zero terms. They would not they would not expect you to find the general term, for example, because it would be actually more difficult. So for that one, what I would encourage you to do for this one, actually, it depends on the function you're compositing with. But for the exponential function, it's not that bad because for the sine, it's just a sum of bunch of the odd polynomial, isn't it? So it's going to be x minus x cubic over 3 factorial, x to the power 5 over 5 factorial, minus on and on and on. That is great. But you know what? For the first 3 non-zero term, I'm going to just attack on the first 2 terms of the sine function, and let's see what I will do. So here, as you can see, you can make an approximation of that function. How? So it's going to be approximated by e to the power of x minus x cubic over 3 factorial plus x to the power 5 over 5 factorial, on and on and on, because that's the Maclaurin series of a sine. But you know what? Let me just get rid of the third one. So I'm just going to narrow it down to the first 2 terms of that. And using the property of the multiplication law here, it's just this is going to be same as e to the power of x times e to the power of negative x cubic over 6, isn't it? So then what you can do is to come up with the Maclaurin series of the second term using the substitution. I had a problem with the initial problem because I have a problem with the initial approach because I didn't have a polynomial. But now you do. So then you can easily substitute. Well, that's not that bad. So, you know, so exponential here is going to be, what is it? 1x squared over 2 x cubic over 6. Goes on and on and on, of course. It's a power series. And then for the second one, my friend, I simply have to substitute with the negative x cubic over 6 in the location of the x. That is great. For the second one then, my friend, is going to be who? It's going to be replacing the x with the negative x cubic over 6. So it's going to be 1 minus x cubic over 6 plus on and on and on. So that is great. And what are you going to do? Very good. I'm going to just distribute. Right? And then, as you can see, very likely that it's going to involve the, the constant term, linear term, and likely the square, right? So then you can combine those coefficients to represent the 3 non-zero terms. So here's the thing. Yes, that the question number 1 could have been easily changed into the Maclaurin series, and what's very popular for the Maclaurin is to work with the composition. Okay, so make sure you are able to composite and then use the distribution for this one also. And another popular composition is, this could have been logarithmic function composition is also very popular. So what I'm saying here is CF to compare, and then, for example, of 1 plus sine x could have been also another solution, another question, and that one is also interesting. Even more interestingly, then 1 plus cosine x, that's even more interesting. So, have a look at this composition and see if you can derive their Maclaurin series without using differentiation. No problem, no problem. You can just differentiate and plug it in 0. That will be the first practice. But as you practice more with the Maclaurin series, you should really grow accustomed to use substitution, because that's the whole point of the chapter. Okay. That's great. Let's have a look at the question number 3 of 2022. Sorry. Yeah, 22 November. Yeah, you're right. And then this was a proof question, you see. So yeah, it was just to check with the algebra, whether you can expand that and then simplify with the common denominator and can go to the right-hand side. So this is the comparison between the left and then the right. That's great. And also, what I think you had to say was that because of the Pythagoras theorem, if you have 3 sides A, B, C, okay, where it holds this relation, it implies it must be a right angle triangle, right? So this is known as the converse of the Pythagoras theorem. And you can directly say, so I was given that these are the 3 sides of what? The right angle triangle. And I do know that has to be my hypotenuse. Why? Because if you square these 2 and add them together, that becomes the square version of that. So by the Pythagoras theorem, that has to be the hypotenuse that leads these 2 to be the base and height. Hence, I can use that for the area of a triangle, right? Sure, that was like the brief summary of that problem. But of course, what do we want to do? Something unholy about this problem. So let's get to it. So unholy version of it is that I really wish that they're going to give some sort of a paper 3 Pythagoras theorem proof question. I really hope, and there are many questions regarding with the Pythagoras theorem. There's one with the the area, the typical area of a square with the some of the smaller four right angle triangles and etc. Or the geometric series problem with the use of the similarity or use of a calculus. There are often some integration method to work with the Pythagoras theorem. So there are many different kinds. That's why it's so popular. But also we can do by contradiction. So let's have a look at the contradiction problem with the Pythagoras theorem. Okay, because contradiction is very popular for the AA. It's like the perk of the proof by deduction. So let's get to it. So if I want to go by the proof by contradiction, what I'm going to say, so yes, I do have a right angle triangle. With the side of A, B, and then the hypotenuse C. So that is great. And for the contradiction, I'm going to assume the opposite. So what I'm going to say, suppose what is true, A squared plus B squared ain't the C squared. Okay? And even better, I will give you better, if it's not the same, either it's less than or bigger than, isn't it? So I'm going to say, without loss of generality, I'm going to assume it ain't the same, so one of them has to be bigger. So I'm going to assume that what this is A squared plus B squared is bigger than C squared. It's sum of the sum of squares of the two sides must be bigger than I'm claiming than the square of the hypotenuse. Okay, that's great. Let's get to it. So if this had been the paper 2 problem, I guess paper 1, paper 2, section B problem, they would have given you to draw an extra line like this. So let me quickly give you a hint. So I'm going to draw an extra line like that, okay? And then I have right angle triangle number 1, number 2. So I would probably write the extended line like that as the height, where it makes the right angle. So they are similar, aren't they? Well, similar, yes. Similarity is going to be great. And here also, number 1, number 2 are right angle triangles. So we hold this property, doesn't it? So I'm going to use this property, though something that I assume to be correct, is going to be the use of the Pythagoras theorem. But for that, I need to know the adjacent here, the opposite here, so doesn't matter. I'm going to call it as x, and that is going to be c minus x, isn't it? So that is great. And then if I use the Pythagoras theorem there, it's going to give me x squared plus h squared is equal to a squared. That is great, right? And number 2, if you look at the number 2, I know that's going to be c minus x squared plus h squared is going to be his hypotenuse of the right angle triangle number 2, isn't it? So that's going to be b squared. Voila. That is good. Oh, sorry, it's not equal to. You're absolutely right, because something that we assume that these hypotenuses are going to be always smaller. Okay, very good. So what I'm going to do then is, you already know the answer. For the proof by deduction or deduction or induction, you already know sort of the answer where you want to show. I know that I want to show something contradicting to my assumption. But either way, I do know that I have to associate with the sum of a squared and b squared. So maybe what I like to do, they didn't tell me, but I would probably add on my own. So that's the science of deduction. You need to know which step I have to take, right? So no one is telling you. So we need to get that hints from our own. That's the science of deduction. That's the deductive science, which is the mathematics. So I'm going to add the right-hand side here. I'm going to get a squared plus b squared. And it's going to be less than, because all positive here, they're all perfect square with the real number. So that's great. So it's going to be then definitely less than the sum of these two here. So it's going to be 2h squared plus, if you expand that, that's a c squared minus 2cx plus x squared. So I'm going to have 2x squared. C squared minus 2cx is what I've got. But obviously, in order to show something opposite, what I want to show is maybe, if I could possibly do so, try to simplify the other side to be just c squared alone. And for that, yes, you want to use also another property of the right angle triangle of that kind. It's going to be similar, right? Number 1, number 2, or very large are going to be similar. So I'm going to work with their gradient. So what I'm saying here is, look at this. So maybe I'm going to use the gradient over here, the rise over run. That's going to be h of x. So using the similarity, which is true, right? So similarity. I'm going to do the h over x So that is a great. And then what's going to be the same gradient here? I believe, sorry, it should be coming from here then, right? So it's going to be c minus x over h. That's great. C minus x over h. That's the same gradient, right? Because the complementary angle, the sum of those two angles has to be 90. All right, that's great. So because then I can do cross product. So h squared is going to be cx minus x squared. Oh, hold on a sec. I see the room of a substitution. So it's going to be 2h squared is equal to 2cx minus 2x squared. Brilliant, because if I sub it in, 2h squared represents the negative x squared, so it's going to cancel out with this one, and it's going to cancel out with the negative 2cx because it's a positive 2cx, then boom, boom, boom. Then on the left-hand side, I'm only left with c squared is bigger than a squared plus b squared, which is a contradiction to what I have assumed. So I know that is wrong because that will lead into something absurd. And you can do the same thing. You can now check with the opposite case of c squared bigger and then derive that c squared is actually less, right? And then either way, neither this is bigger nor smaller, has to be same is what you're going to do, the proof by contradiction for the Pythagoras theorem. So, I think the question number 3 was talking about the right angle and Pythagoras, and that's all good. And I wanted to show there are many proofs of the Pythagoras theorem, including the contradiction. So I wanted to share you with the unholy version of it. Obviously, there are many kinds. It's one of the most popular theorem, isn't it, in math? And it can be like a subdued version of for the paper 3. So please pay a key eye on the Pythagoras theorem and its very, very various proofs. Okay, so let's move on. So the question number 4 of the 2022 November was working with the integral, right? We have to find the general solution and find the particular solution using the initial condition of 1,5. Okay, no problem. It's pretty trivial, isn't it? Because you know that I have to make the substitution, right? So yes, I guess they didn't give you the substitution, but come on, it's got the quadratic and linear, and it looks like the multiple of the derivatives, and very tempting to work with the substitution of the denominator, isn't it? So that's fine. That's very trivial here. So what we're gonna do is to keep our business clean with some version of the extended version of the integral of that kind. So yeah, the very first thing is you saw the linear of a quadratic, but if you have a constant of a quadratic, there are two versions of a constant of a quadratic that are very popular for the exam. The one is, yes, use of the factorizable one. So for the constant of a quadratic, I got the 5 over, what is it? I'm going to factorize it. Then it's going to be x plus 3, x minus 2, isn't it? So that's great. And then if it's factorizable like the linear like this, what you want to do is to use a separation of fractions. So make sure to memorize this. 1 over AB is the same as 1 over B minus A, 1 over A minus 1 over B. So that is great. So I can do the same thing here, right? Then who do you want to call the B? So for me, I would call the B as the x plus 3. Why? Because it wouldn't give me the negative. So I prefer working with things with the positive. And yes, remember multiplication is commutative, so it doesn't matter even if you change the order of the multiplication, right? So that's not that bad, yes. And then what I realize here on the right-hand side, then using that, so 5 comes out because it's a constant coefficient. And then I'm going to integrate 1 over. If you see their difference, it becomes a 5. And then it's going to be 1 over x minus 2 minus 1 over x plus 3, according to who? The separation of fraction. And that's lovely, isn't it? Because I can cancel out the 5. Boom, boom. So that is great. So what you are going to end up having here is 1 over x minus 2 minus 1 over x plus 3. So that's great. Then it became a very typical rational function of a linear kind. So I'm going to have ln absolute value of x minus 2 minus ln absolute value of x plus 3 plus c. But however, don't forget, you can simplify further if you see the difference of log. So I'm going to be putting ln as a fraction one, like the a over b. So, that will be the simplified version. So if you have a constant of a quadratic, very popular to be either factorizable or not factorizable. But if it's a factorizable, please work with the separation of fraction, okay? But yeah, you know, like this quadratic here with the square root is also very popular. If this one may not be factorizable, then in that case, as you remember from the quadratic, I gotta do the completing the square. So let's have a look. So here, if I do the completing the square of the denominator inside, I'm going to do what? Let's factorize by the -4. Boom. Then it's got x squared plus x. Oh la la. So what I'm going to do is to halfen the coefficient and square it. So plus 1/4. So when it comes out, it's -1, but I want to have +8, so I'm going to add by 9. Very good. So I'm going to try my best to put it into the perfect square form. So it's going to be 3 squared minus 4 x plus half square. So that is great, but I want you to remember cleaner the better, simpler the better. So if I put the 4 inside, it becomes the factor of 2, so it becomes minus 2x plus 1 squared. So that is great, isn't it? So then I'm going to plug it in here. So that's the more simplified version of it. So then I have, oh la la, hold on a sec. So I got the 3 over square root of 3 squared minus 2x plus 1 squared dx is my integral. So that's the more simplified version of it. And I want you to make sure you see now that it's going to be this is going to be giving you the antiderivative of that is going to be the arc sine x, right? Remember, so what I want you to remember are two things. So integral of 1 over square root of a squared minus x squared dx is going to be integral of, it's going to be the same as arc sine x over a plus c. So that is great. But the integral of 1 over a squared plus x squared, don't forget to multiply the coefficient with the 1 over a. It's going to be 1 over a arctangent. Very good. The x over a plus c. So please notice the difference. Notice the difference of having the coefficient or not having the coefficient. Okay, so that's very important to distinguish. And one more thing. And also, remember, if you already know it's antiderivative, but you got the linear substitution inside, it must come out as the reciprocal. Do not forget, that's a very common mistake, and I don't want you to make it after having watched this video. All right, so for this one, I know I don't need to make fancy substitution. You could have let the 2x plus 1 as a 3 sine theta. I don't mind you trying it, but I don't have to because I already know it's antiderivative version of it. So I know then 3 coefficient comes as it remains as the constant coefficient, and this is going to directly have arc sine. And what was my domain? It was a 2x plus 1, who's the row of the a, 3 squared, then boom, is got what I have. But however, please be careful, I have a linear substitution. It's because of the third property there, who needs to pop out. Very good, half must pop out. So it's going to actually become 3 over 2, and then the arc sine, boom, is what I've got. So that is great. Okay, so that is what I have. Good, so please make sure if you see the square root of a quadratic form, very likely, almost every time, that it's going to be something with the arc sine. Same thing for the without the square root, it's very likely to be working with the the arctangent. So let's see. So I'm going to do the completing the square here. So if I factorize by 4, I got the x squared minus 6x. I want to add by 9. That's a 36. To make it 61, I got to add by 21. That is great. So it's going to be 4x minus 3 squared plus 25. So that's going to be, again, if it's possible, please put it inside. So it's going to be, well, every time, please put it inside. So it's going to be 2x minus 6, righto, squared plus 5 squared. That is great. So this integral is going to be from 3 to 5.5. And then, my friend, the denominator is going to be given as who? Like that. That is great. And then on the top, it's going to be 10. Dx is what I've got. That is great. Okay. Oops, sorry. So I'm going to erase this. Okay, so that is great. And then what I want to do here is to perform the integral right away. Because you already know, we already mentioned of the antiderivative of that is going to sum up in the arctangent. So no problem. So I'm going to take the 10, very good, and I'm going to have arctangent. And who's going to be my domain? It's going to be 2x minus 6 over 5, because that was my a. But he had to come out, wasn't it? So 1 over 5. And not to mention this linear substitution, coefficient is going to come out as a reciprocal, so I'm going to multiply by 2 in the bottom as well. And don't forget, this is a definite integral. I'm very keen on evaluating from 3 to 5.5. That is great, but luckily now I can get rid of the 10 because I got the denominator 10 from the antiderivative. So then I'm going to start plugging it. If you plug 5.5 on 2, it becomes 11. Minus 6 is 5. So 5 over 5 gives you arctangent 1. That is great. If you put 3, that's 0. Arctangent 0 is 0. So that will be simply just pi over 4. Okie dokie. So yeah, that's how we get with this integral. So please be careful. If you got a quadratic, things sometimes factorizable or not factorizable. Either way, it's going to be separation of fraction or the completing the square. Okay. Let's have a look at this one. So on the initial question from the 2022 November, on question number 4, it was the linear of a quadratic. But what if I have a quadratic of a quadratic? It's in the syllabus, right? It's going to be working with the long division and the partial fraction. So if possible, but in this time it's not going to be partial fraction. Let's just divide. So if you got the same degree or bigger, you can always divide further. So I'm going to try to do this by the long division. So it's going to be x squared plus 3, 1. X squared plus 3, I'm going to subtract, so it's going to be 5x minus 2. Can I divide further? No, because your remainder has a smaller degree than what you're dividing by. So my quotient here is going to be 1, my friend. So it's going to be integral of 1. And my remainder now became 5x minus 2 over x squared plus 3. And dx is what I've got. All right? Then it's quite similar to the question number 4 in the exam. But what is slightly more difficult here now is the existence of a constant on the numerator. Okay, so let's discuss this a bit more. So here I'm trying to integrate, but however, its derivative on the denominator is a 2x. It does not cancel out the numerator right away. If it had been just a 5x, it does cancel out the x. It's beautiful. So it's going to be simple logarithmic form when you integrate. However, I still have the constant 2 there. So the derivative does not justify. So what you need to do is to separate them. I would divide the 1 by 1, in fact. So I'm using the linearity of integral. This is possible. How? 5x over x squared plus 3 dx. And then minus 2 integral 1 over x squared plus 3 dx is what I've got. Right? So I just did the 1 by 1, you see. So a plus b over c is a over c plus b over c. That's exactly what I did. And I took out the constant factor for the second one. And then it's fine, right? So for that one, it's going to be the logarithmic form. If you came up with what? The u to be x squared plus 3, that is great because its derivative is a 2x and it cancels out to 2. You may have some constant coefficient like the 5, but it doesn't matter. It's constant, so it's okay. So here we know if we make the substitution, that would have been 5 over 2, then absolute value of x squared plus 3. So that is great. And then the second one now, this 3 is the same as what? Root 3 squared. So it's got the sum of squares. Now you know it's going to induce the arctangent. So that is lovely. So I'm going to have, what is it? Minus 2 over root 3 arctangent. And who is my domain? X over root 3 plus c is what I've got. So make sure you're able to do this with the long division. And still, after having done the long division, you may still separate with the quotient, with the remainder. Yeah, so you're going to plug it in here. And then don't forget, the integral of 1 is simply just x. And that's going to be the integral of such kind involving with the long division as well. So for this one, yeah, this may not be long. This is not divisible, of course, further because it's got the linear and the quadratic. So we cannot divide further. However, it is factorizable, isn't it? It's because I got the x plus 1 over, what is it? The x plus 2, x plus 3. That is lovely here. And then, you do the partial fraction, isn't it? So you know that I'm going to be keen on, what is it? A over x plus 2 plus b over x plus 3 dx. I'm going to do then trying to compare the numerator by putting in the common denominator, you see. So a x plus 3 plus b x plus 2 is what I've got. And I want that numerator to be the same as x plus 1. You may do the long division, you may expand all and then compare with the coefficient of x in constant term, or you can just plug the values in. It's just a simple simultaneous equation. So I'm going to let x to be, for example, let's make negative 3 Why not? Because then if I did, then left-hand side is going to be negative 2. Then this one becomes 0 because this vector became 0. So that's going to be negative b. Voila. B is simply just 2. And then, you know, what's going to be the second x that I would plug it in to simplify the equation? Can you tell me that? Very good. I'm going to put negative 2 there. So let's do that. So if I did, on the left-hand side, I got negative 1. On the right-hand side, that's going to be negative 8. Then voila, a is going to be simply just 1 is what I've got. So now the integral is actually quite nice because you can then integrate with the 1 and 2, and that's going to come out as log, that's going to come out as log. Everyone is happy. Okay? So, yeah. And also, you know, like the one that we saw from the quadratic is the either separation of variable or use the arcsine or arctangent, but maybe you may see some of the questions that we are not familiar with, and that's not bad because you still learn the recursive formula. So I want you to please remember, whenever we see a squared minus x squared in the integral, it might be, it does not always guarantee, but it may be to associate with the trigonometric identity, isn't it? Because for that one, I'm going to like x to be a sine theta. And then for the second one, if I had x squared minus a squared, x equal to a secant theta. And then for the third one, if I have some of the squares like that, then yeah, substitution is very likely to be with a tangent theta. So that is a great. And yes, you know, it's very likely that they're gonna give you which one to substitute. So let me give you one. So here I want to ask you that let the x to be 4 secant theta. Then let's then try to see the solution using the substitution here. So often this trigonometric substitution leads to the extension of the trigonometric identity, especially the Pythagorean identity. So I want you to be very good at it. So let's try to substitute. Before I substitute, maybe I want to simplify here by taking out the square root of 3. So this is a 1 over square root of 3, integral 1 over x square root of the x squared minus 4 square dx. That is great. And then before I'm making the substitution of that, I need to convert everything. I'm trying to convert everything in terms of theta. So that is great. So I got the first one here. Now I'm going to do what? Dx over d theta. And now this is the time to check whether you have practiced your rules of differentiation correctly. So derivative of secant, you should memorize it. It's a secant theta times tangent theta. That is great. So then this suggests that dx is going to be who? Secant theta tangent theta times d theta. Voila. And very, very good. Okay, muy bien. So it's going to be d theta here. That is great. And then let's then try to plug it in. So why not? So it's going to be 1 over root 3. Oh la la. So boom, 1 over square root of what am I going to factorize by? I'm going to factorize by the 4 square. Oops, oopsie-doopsie. Then it's going to be secant square theta minus 1. And then the dx, we rearranged beautifully. So I'm going to plug it in here. So that is great. Then let's dig in further, my friend. So now I see, oh, okay, hold on a sec. Who's going to be a perfect square? 4 square is a perfect square, so it's going to come out as a 4. Okay, so that denominator part is going to be 4. And don't forget, my friend, the secant square minus 1 using the Pythagorean identity is tangent square. So if you square root on it, what do you get? Voila, I get the tangent x. Okay, that's beautiful. So of that integral, it's going to be 1 over 4 root 3. I'm very keen on putting all the constant coefficient outside because I don't want to meddle with the integral. And then I've got the secant theta, tangent theta on the top, my friend. And then the denominator, I get just simple tangent theta. Oh la la, then I'm very happy with this cancellation. So you just have to work with the integral of the secant theta, for which we mentioned that we should memorize it. Okay? Yes, in the question, they're going to tell you what to do with to derive the integral of a secant theta, either by giving you the derivative of a ln of a secant plus tangent theta, or asking you to multiply special one like the secant theta plus tangent theta over secant theta plus tangent theta. However, if they have given you, just use it. What was it? This is going to be 1 over 4 root 3 at ln absolute value of a secant theta plus tangent theta using the fundamental theorem of calculus. However, I'm not done. For this typical integral problem, what you have to do is bring it in terms of x. So then, because it's an indefinite integral, right? So then, from my initial substitution, you already know secant theta is an x over 4, right? So I can replace that with the x over 4 right away, no problem. And then, my friend, yes, you're absolutely right. How would you verify with the tangent theta? So you should know how to work with the Pythagorean identity to convert around. But whenever you convert, what I think is more comfortable for me is to work with the right angle triangle. So if I got the secant theta as x over 4, I know cosine theta, which is the reciprocal of a secant, is a 4 over x. So that means my hypotenuse is going to be x, my adjacent is a 4. So my opposite using the Pythagoras theorem is going to come out as a square root of x squared minus 16. If I let this to be theta here, and this is a right angle triangle, and what am I trying to get? I'm trying to get the tangent theta, sorry. Then I can just simply get the tangent theta from there, which is going to be the rise over run. So x squared minus 16 over 4 is what I've got, and that is the good integral. So it's very popular. I kid you not, use of the trigonometric substitution is going to be given, but you need to do all the algebra of making the substitution, being able to integrate with your knowledge of the integration and conversion in terms of x using the Pythagorean identity. So please train. So that's the unholy version of the integration of the question number 4. So let's continue.